Today, I will be presenting CCCP, Secure Remote Storage for Computational RFIDs. This was initially presented in the 2009 Usenix Security Symposium. So I'm sure we've all heard of RFIDs before. RFID just stands for radio frequency identification, and it's just a method of storing and accessing data through electromagnetic transmission to an RFID tag. RFID tags consist of a chip and an antenna, and they carry data that's usually some sort of unique identifier, and the RFID reader sends out radio waves and receives signals from the tag, decodes the data, and sends the data back to the host. Computational RFIDs are a subset of these passive RFIDs, and when I say passive, that means they do not have a power source. So passive RFID tags receive all their power from the reader's electromagnetic field. So this means that the CRFIDs cannot only send the data to the RFID readers, but they're also programmable and can perform computations, given that they have access to power. So CRFIDs operate on harvested energy, and they store that energy in capacitors, but over time those capacitors leak energy, so even if the energy isn't used by the CRFID for computation or whatever, it will eventually deplete over time. Some of the general challenges faced by CRFIDs are the flash memory limitations, the non-autonomous operation, and the unsteady energy supply. So CRFIDs typically use flash memory for data storage, but that requires a significant amount of energy to do flash writes and erases, slightly less energy for reads, but it's still pretty energy intensive. And since the CRFIDs rely on harvested energy from the RFID reader, they're not autonomous, and therefore they're limited in their operational range. And since RFID readers do not adhere to any particular energy delivery schedule, the CRFID has an unsteady energy supply that might vary. So the capacitor needs to be able to manage that unpredictable power. So since CRFIDs don't have a guaranteed consistent energy source, the computation is likely to be interrupted. On top of this, any physical changes like obstructions or physical barriers might interfere with energy harvesting and computation, the same as any other RFID. So therefore, a lot of times there are operational constraints that are placed on programs that are being executed on these CRFIDs. So it might be restraints like it has to hold the tag has to be close to the reader for X amount of time. And that's not really ideal for general use CRFIDs, since it gives a specific use case, and maybe those constraints aren't always able to be met. So the big goal of this paper is to address this by completing computation across multiple energy cycles. So this is implemented in this paper as something called CCCP, Cryptographic Computational Continuation Passing. So an obvious way to spread the computation across multiple power cycles is to save state in local non-volatile memory. But this is pretty undesirable because, like I mentioned before, writing and erasing flash requires a lot of energy, and reading flash requires a significant amount as well. So therefore, instead of imposing usage restrictions or using expensive flash options, CCCP proposes that a CRFID can use external resources for storage. So essentially, it's a secure remote storage technique that allows a tag to checkpoint its computational state on an untrusted reader, and it uses radio to do this. So this graph over here, you can see how much more expensive it is to write to flash, or even for CPU, and radio requires the least amount for these CRFIDs. So some of the major design goals for CCCP revolve around computational progress and security. So to address computational progress, CCCP implements remote checkpointing to prevent computation or data loss whenever the power is lost. And overall security is a major concern, but the 4 specific facets that we're going to focus on for this are authentication, integrity, data freshness, and confidentiality. So to address the authentication and integrity concerns, universal hash function based message authentication codes, so UHF MACs, are used to ensure that the data is not being modified during the checkpointing process. And they're pretty lightweight and well suited for low energy environments. So for that reason, these UHF MACs are used. To address data freshness, keys are unique and only generated once. Also, CCCP introduces something called the hole punching technique, and that's used to manage counters that are updated with every operation, so somewhat like saving state in a way. So rather than using typical binary counters that require blocks of flash memory to be modified, which is an expensive process, unary counters are used since they're more efficient and they're only used once. So the little example in there on the slide, you can binary 1, you write a 1 in the rightmost slot, same thing for unary, but then you have to erase and then write to make a 2 in binary, but for unary you just change the 0 to a 1, so that requires less energy. And to address confidentiality, CCCP uses symmetric key encryption. So that's more efficient than asymmetric key encryption since the same key is used for both encrypting and decrypting, and clearly efficiency and energy usage are key components of this work. So symmetric key is used here, and the cryptographic keys are pre-computed. So basically whenever there's plenty of energy available, so whenever the CRFID is near a reader, the keys are being pre-computed and stored for future use. So that means there's always a new key on hand. So the threat model for this work assumes that an adversary doesn't have physical access to inspect the CRFID's memory contents. So with that in mind, it focuses on 2 attacks that our CRFID could potentially address. And these 2 types of attacks are active and passive radio attacks and attacks by an untrusted storage facility. So radio attacks might involve an adversary eavesdropping on radio communication between the CRFID and reader, or it could involve an adversary that's pretending to be an RFID reader to collect the checkpointing data from the CRFIDs. And remote skimmers are somewhat relevant to this, not exactly, because those are more intended just for RFIDs, but that sort of concept applies here. And then also somewhat relevant, not super relevant, but more targeted for RFID is Flipper Zero. It's just a cool little device. It came out way after this paper was published, but it supports various protocols, including RFID. And it's pretty cool and has a lot of uses in security research, but it does have the ability to do things like clone RFID tags and other malicious activities like skimming. However, like I said, these sorts of threats aren't necessarily as applicable to CRFIDs, particularly ones that are keeping security in mind. So like the work being done in this paper, the advanced computational and security capabilities just sort of make this less applicable. But an attack by an untrusted storage facility might involve an adversary pretending to be a reader to send corrupted or incorrect data to the CRFID. Or it could be an adversary pretending to be a particular CRFID to retrieve that particular CRFID's stored data. So in order to prevent these types of attacks, CCCP uses encryption and authentication protocols like we just discussed. Looking into the implementation of CCCP, we can see that it relies on components that are implemented on both the CRFID side and the RFID reader side. So on the CRFID side, the bulk of the implementation occurs. So there are 3 main routines implemented in C. The first of those is the checkpoint routine, and that encrypts, max, and transmits a fixed chunk of the computational state via backscatter. And backscatter communication just reflects existing radio waves rather than generating new ones, so it relies on receiving a signal from the reader first, but it's much more efficient for the CRFID. The resume routine receives and decrypts an encrypted checkpoint and MAC from the reader, and it restores the state of the CRFID if the data is deemed authentic. Just like the checkpoint routine, it also is received via backscatter. And the key refresh routine replaces used key stream material with new material in the non-volatile memory. So this ensures that keys are not reused and that encryption remains secure. The reader, on the other hand, relies on simple control programs, and the messages are manually inspected. Because of the Gen 2 protocol's complexity, not much more was done for the reader implementation. More effort was focused on the CRFID side, since that's where there are more resource constraints. The other part of the implementation is the communication protocol between the reader and the CRFID. So the CRFID is limited in that its only communication hardware is a backscatter circuit rather than an active radio. So like I mentioned earlier, to communicate via backscatter, the reader has to emit some kind of carrier signal. And CCCP leverages EPC Gen 2 RFID commands, and the experiments for the evaluation used 2 compatible RFID readers with EPC Gen 2 that are just off-shelf products, and so not many modifications were made. But essentially the reader will start by issuing a query to set up communication, and then from there the reader will issue read and write commands to ensure that the chunks of checkpointed state are properly encrypted and transmitted. And so to ensure that everything remains encrypted in both ways that it's being transmitted, a MAC is added to each of the messages, and the write commands transmit pretty small amounts of data, so the CRFID might have to end up requesting multiple write commands to be able to transmit and receive that checkpointed state. So CCCP has 4 operating modes that can be considered for evaluation. So the first mode is the simplest. The checkpointed state is only stored in local flash memory. So this is the most secure option since it doesn't rely on any data transmission, external devices, or radio. But like we mentioned earlier, flash-only checkpointing is not always the best option. And this mode is called Mementos, which is based after the system that inspired CCCP. The next mode is CCCP NoSec, so no security additions to it. So the CRFID sends its computational state in plain text to the reader, but sending it in plain text provides an opportunity for an adversary to interrupt and retrieve the transmission of state information. The CCCP authentication mode adds a layer of security. It adds message authentication code to the plain text, and it does this prior to transmitting, and so it's able to offer protection against data modification, since the CRFID has to be able to verify the MAC before restoring that state. And the most cryptographically complex one adds another layer on top of that message authentication code, and so this adds encryption. So by encrypting the computational state both ways, using a symmetric encryption key, this requires the adversary to find both a hash collision and be able to brute force search to find a valid encrypted state. So that adds an extra layer of security. And the mode selection might vary depending on the particular scenario that CCCP is being implemented for. So obviously the modes that have more security features are going to be slightly more energy intensive compared to those without. The measurements of energy consumption for all 4 of the CCCP modes are shown here in this graph. So for data sizes greater than 16 bytes, checkpointing under the CCCP no security requires less energy than a checkpoint to flash. On the other hand, under the highest level of security, so authentication configuration, which adds encryption and MAC operations, that similar threshold exists between 64 and 128 bytes. So there is a slight benefit overall to employing the CCCP mechanism for checkpointing remotely. And now moving into the applications and future work. So outsourcing memory to external devices should introduce more potential applications for CRFIDs because there's less limitation regarding the checkpointing. The paper proposes some examples of these applications like low maintenance sensors, RFID sensor networks, and CRFIDs as smart cards. These applications are still relevant now, and CRFIDs are often used for medical monitoring devices and sometimes for smart environments and further research. But for things like smart cards, like credit cards and things like that, encryption and tokenization and the simpler RFID and NFC technologies tend to provide enough security and functionality for stuff like that. So CRFIDs aren't necessarily used in place of those things. One real application from 2010 which was right after this paper, was NeuralWisp, and that was a wireless neural interface that monitors neural signals and transmits spike density. So that was an actual implementation of CRFIDs with WISP, which is pretty similar to this paper. But since CRFIDs can perform tasks autonomously and even perform computational tasks, there's still a lot of work to be done to be able to reap the benefits in today's increasingly autonomous world. Thank you.